Hey there, this is Bram Bresenham. I just finished week 2 of developing Axor the Mighty in Godot. This week, I began implementing the user interface. I'll show you where the game is at, and then I'll talk about what went into getting there. The game needs robust dynamic layout support for different display aspect ratios on different devices. Notice how the layout changes and adapts as I resize the window to different portrait mode aspect ratios. I haven't done any work on landscape yet. The game won't be changing its layout as it's played on any single device, but it needs to support any size of display. In Axor, the single screen arena is 11 by 11 tiles. The outer wall at the sides and the bottom can be hidden, but the inner 9 by 10 tiles must always be visible. The more tiles that need to fit the width of the screen, the smaller the tiles are. So for shorter displays, I show more tiles wide, and as the displays get taller, I show fewer tiles wide. Any leftover height goes to the top and bottom. We'll come back and take a closer look at the nascent user interface elements on the top and bottom, but for now, let's take a look at how the dynamically sizing arena view is implemented and build the essential idea in Godot. Godot has 3 broad categories of nodes that are used to build scenes: 2D, 3D, and control nodes. Control nodes are designed specifically for user interface needs. The Godot editor is itself a Godot app that uses control nodes to implement its UI. Whenever you start a new scene, you can pick any type of node to be the root node of that scene. Choosing a 3D node type will cause the display, technically the viewport, to be set up for 3D rendering. And choosing a 2D node or control node type will set up the display for 2D rendering. It's possible to have additional 2D viewports within 3D scenes, and vice versa. There's an additional twist. In Godot, you can turn any subtree of nodes into its own scene, which can then be treated as a new node type, replicated, and customized in main scenes or other scenes. Scenes are like node templates, similar to Unity prefabs. For instance, each individual sand, lava, and wall tile in Axor is an instance of those 3 separate scenes, each its own collection of nodes. Let's make a new scene. Pick User Interface, which starts us off with a basic control node as the root node. Deselect the control node, and in the editor view window we see red and green origin lines, as well as a blue bounding box that indicates the initial size of the viewport, which matches the window resolution in the project settings. Select the control again. We see a bounding box with red handle dots and green anchor spikes. More on those later. But notice that the control expands to fill the entire viewport by default. There are 2 broad types of control nodes: controls and containers. Containers are control nodes, but they have the added duty of laying out their child nodes in some arrangement. Containers are used for layout, and other controls are the visual and interactive elements. Add a color rect. It has a small little bounding box. Let's have it take up the entire space of its parent node. Adjust Layout mode to Anchors, and then select Anchors preset Full Rect. Change the color to red. Note how you can type F00 as shorthand for FF0000. I love that convenience. Color rects are great as placeholders for building layouts. They're easy to add, and they make it easy to see what's where. Make 2 copies of the color rect and change their colors to green and blue, 0F0 and 00F. On Mac, I'm typing Command D to duplicate. Right now, all we see is the blue color rect. The root control node isn't a container, so it's not doing any layout. Each child just gets stacked on top of the previous one. Add a VBox container to the root. It will lay out its child nodes in a vertical column. Like the color rects, it is very small to start with. Set its positioning to anchors and its anchors preset to full rect. Drag the 3 color rects under it in the scene panel, and voila! Everything disappears. This is one of the quirks of Godot. One would hope that new items dropped into the container would have some kind of reasonable initial settings applied, but no. The control rects have no minimum size, and so the container treats them as size 0. We could set a minimum size on each, or we could set the vertical expand flag under layout container sizing. Let's do a bit of both. Set the green color rects custom minimum Y size to 200. And it pops up to that many pixels. Turn on expand for red and blue, leaving their custom minimum size at 0. Run the scene, Command R for Mac, and play with the window size to see those settings in action. Note the gap between the 3 elements. That's due to the default UI theme. Let's go back to the VBox container and turn on the layout theme overrides constants separation value, leaving it at 0. So, this was my starting point. The next step is to add a script that adjusts the custom minimum size for different aspect ratios. We'll say that the green color rect will be the tilemap view of the game. Let's say that we want the tilemap view to show 11 by 10 tiles, 10 by 10 tiles, or 9 by 10 tiles, depending on how tall the display is. Let's add a script. I'll call it viewsizer.gd. In ready, we'll connect to the viewport's size changed signal. And then also call the callback directly to set the initial size. In the callback, we'll calculate the size for the tilemap view. Let's start by hard-coding the first case, 11 by 10 tiles. We'll get the current display size from the viewport's visible rect. The tile size will be the display width divided by 11. The tilemap view width will be the same as the display width, and the height will be the tile size times 10. Now let's modify it to use a 10 by 10 tile view if the screen is tall enough. But how tall is tall enough? What's the threshold? We'll need to check the vertical aspect ratio of the display. Aspect ratios are usually expressed as width over height, but for this scenario we need height over width. I call that a vertical aspect ratio. iPad is the shortest portrait mode device I know of, with a vertical aspect ratio of 1024 over 768. That's the same as 2048 over 1536, which is the same as 600 over 450, which is the same as 4 over 3. They all work out to be 1.33. We can choose any of these widths to be our reference width for our calculations. 3, 450, 768, or 1536. I'll pick 768. So, on an iPad-sized display that's 1024 pixels tall over 768 pixels wide, I want 11 by 10 tiles. The tile size will be 69.8 pixels, and the tile map view height will be 698 pixels. That means we have 1024 minus 698 equals 326 pixels left over for the user interface on the top and bottom. Now, as the display gets taller and taller, the view height will remain 698 pixels, and the extra pixels will go to the UI. How much taller does it have to grow before we can switch to the larger 10 by 10 tile view and still have at least 326 pixels left over for the UI? If the width is still 768 and we are showing 10 by 10 tiles, each tile will be 76.8 pixels wide and the tile map view height will be 768. That's 70 pixels taller than the previous tile map view height of 698, so the display height needs to increase from 1024 pixels to 1094 pixels. 1094 minus 768 again leaves 326 pixels for the UI. So the vertical aspect ratio where we make the switch is 1094 over 768, or 1.42. That fraction works correctly no matter what the actual screen width is. The second threshold to switch to 9 by 10 tiles ends up working out to 1179 over 768, or 1.54. Let's add those thresholds to the sizing logic and try it out. Now let's look at the top and bottom UI areas. Notice how the metal frame of a UI area isn't stretching in a way that distorts it. The top and bottom are fixed height relative to the width of the window. The sides are stretching, but there's no prominent marks on the sides to give it away. Also note that the background texture isn't stretching either. It's scaling while retaining its same aspect ratio. These metal panels are made out of 4 pieces: top, middle, and bottom frame pieces with a transparent interior and a separate background texture. Let's implement one of these panels on the practice UI we've been building. Let's take advantage of the node subtree system and work on the entire top panel as a separate scene. Right-click the red color rect and save branch as scene. I'll call it panel. Then click the movie clapboard next to it to edit that scene. The red color rect is now the root of the new panel scene. Its layout needs a little fixing, which makes sense because it used to be in a container and now it's on its own. I'll right-click and change its node type to be a texture rect. I'll add my background image as the texture. I'll set the expand mode to fit height proportional to get rid of the overhang, and the stretch mode to keep aspect covered. I'll create a VBox container child, set it to anchor full rect, and override its separation to 0. I'll add 3 more texture rects to the VBox and set their textures to be the 3 pieces of the frame. The top and bottom get set to fit height proportional, while the middle gets set to ignore size. Otherwise, its minimum height would be the height of the texture, and it wouldn't shrink down nicely. The middle piece also needs its expand flag set. Looks good. Now back to the main UI scene and bam! Fully working panel. Let's delete the blue bar and replace it with a copy of that panel scene and bam! 2 working panels. Piece of cake. That's the power of scene nodes. Now let's add an info pennant with text. Let's start with a new scene and choose a texture rect as the root. Fix the anchors. Rename the root to pennant. Assign the pennant texture and save the scene. Go back to the UI scene and add an HBox container as a child of the top panel. Anchors, full rect. Now we need to add the pennant scene as a child of the HBox. Either right-click on the HBox and pick Instantiate Child Scene, or go down and find the pennant scene file at the bottom and drag it up on top of the HBox. Expand node, fit width proportional. Set the expand flag, then change horizontal fill to be shrink end. Go back to the pennant scene and add a rich text label. This part seems simple enough, but it's quite tricky, at least in a dynamic layout. For now, drag the bounding box to place the text in the middle of the pennant, leaving the green anchors where they are. Enable BB code so we can add tags into the text. Set the text to be center in square brackets ABC. Turn off scroll active to prevent the scroll bar from appearing. Go under Control Theme Overrides Font Sizes, enable a normal font size override, and pick a text size that looks good. Now switch back to the UI scene and it looks nothing like it's supposed to. The text hasn't scaled down and it's way off to the side from where it should be. Actually though, in both scenes the text is in the same position relative to the anchors. Let's fix the anchors and then I'll explain them. Go back to the pennant scene and drag the bottom left anchor onto the bottom left red dot, and then the top left anchor onto the top left red dot. This will automatically move the other 2 anchors to the corresponding corners. Save and switch back to the UI scene. That's closer. The text is now technically in the right place, but the font size hasn't scaled with the pennant size. There's no built-in simple solution for this. Rich text labels were simply not made to be scaled. I understand that regular labels work fine, but I haven't played with them yet. Still, we can hack in a solution with a node script. Go to gist.github.com/brombrez and download my autoscale RichTextLabel.gd script. Go to the pennant scene and drag it onto the rich text label. It's a tool script, which means 2 things. First, that it will automatically set a necessary property, and second, that we need to save and reload the scene for the tool to activate. I do so. Notice how the node reference height property is now set. Switch back to the UI scene. The text doesn't look any different, but that's because the font is only scaled at runtime. Run the scene and the text looks perfect. To have it look better in the UI scene, we could create the pennant scene at a size closer to the size it will be in the UI scene. Let's talk about those anchors. Back in the pennant scene, I'll set the RichTextLabel anchors to full rect. Now I'll move the bounding box so that it's roughly half the width and half the height, with the corners at roughly the 25% and 75% marks. Switch the anchors preset to custom and we'll see additional info. Notice the anchor offsets, left and right, are roughly 110, top and bottom are roughly 140. This is versus my default window size of 450 by 600. These offsets are not computed values, these are absolute pixel margins. The top left corner of the bounding box isn't 25% of the way in the pennant, it's 110 by 140 pixels in. The bottom right corner isn't at 75%, it's minus 110 minus 140 pixels from the bottom right parent corner. So if the pennant becomes half size, or any size, the text box is still at 110, 140 pixels from the top left corner. I'll turn off the centering and the auto text scaling and demonstrate. If we move the anchors to these corner points, now we get the behavior we were expecting. The top left anchor is at roughly 0.25 and the bottom right is at roughly 0.75, which means that no matter how big or small the pennant gets, the RichTextLabel bounds run from 25% to 75% of its parent. Also note that the anchor offsets go to 0 when we move the anchors in. That's good. We don't want pixel margins of absolute sizes in a dynamically resizable layout. So, think of the green anchors as the corners of a bounding box relative to the parent node, expressed as proportions, similar to percentages. The red dots and the orange bounding box indicate absolute pixel offsets, or margins. The margin bounding box is easy to position, so in general, position it first, and then drag the green anchors to snap to its corners. Alright, that's a wrap on week 2. I'll be back next week. See you then.